Hi everyone, I'm Meng. I'm going to talking about building scalable zero-knowledge proofs for nonlinear functions in machine learning. This is a joint work with Hanxiao Chen, Hongwei Li, Chenkai Weng, Yuan Zhang, Haomiao and Tianwei Zhang. Machine learning-based inference services have been widely employed in real-world scenarios. In this setting, the client submits a query. Then the server performs the inference and returns the results to the client. However, the inference process is a black box to the client, and the server may be malicious. So a natural question is how to validate the service integrity. Particularly, the inference results are indeed generated by an accurate machine learning model with a correct specification. A promising technique for this goal is zero-knowledge proof. In zero-knowledge proofs, we have two parties, prover and verifier. The prover convinces the verifier that he knows a witness W such that the result Y is computed on W. There are three important properties. The first is the completeness. If the prover correctly computes the result, then the verifier should be convinced. The soundness means that if the result is incorrect, there is a negligible probability that the verifier will be convinced. The zero-knowledge literally means no information is revealed except for the result. However, existing zero-knowledge proofs for inference are not sufficient. Machine learning model is comprised of alternating linear and nonlinear layers. The linear layers include convolutional and fully connected layers, while the nonlinear layers include ReLU, GeLU, softmax, max polling, and normalization. As shown in recent work, mistake, the performance bottleneck is the computational cost, mainly coming from nonlinear layers. For example, the evaluation of nonlinear functions consumes about 8 minutes for one inference on the ResNet model, which accounts for more than 80% of the total inference runtime. This is caused by the heavy arithmetic Boolean conversion and the Boolean circuit evaluation of nonlinear functions. To address this efficiency bottleneck, we propose a new zero-knowledge proof framework for nonlinear functions using the perspective of table lookup. This framework consists of 3 levels, namely building blocks, mathematical functions, and machine learning applications. The evaluation results show up to 2 orders of magnitude runtime improvement, while achieving a comparable communication cost. We first explain how the lookup table is used in zero-knowledge proofs. The prover and verifier have a public table. It stores all input-output pairs of the function f. Then the prover can convince the verifier that the computed output y, along with its input x, exists in this table. We use 2 existing lookup techniques. One is check lookup. It checks the witness is an item of the public table. The other is check range. It means checking the witness belongs to a given range. However, there are 2 challenges. First, the table used in machine learning is very large. For example, the table includes items of 2 to the 60 power. This will seriously affect efficiency. A potential solution is to decompose larger input into several smaller digits. Unfortunately, it's non-trivial to use these smaller digits in zero-knowledge proofs, while ensuring result correctness and proof soundness. So we design new zero-knowledge proofs carefully using these decomposed digits. So the most important part of our framework is building blocks. We take digital decomposition and comparison as examples. To address the prohibitively large size of lookup in machine learning applications, a natural idea is to decompose the input x into several small digits x0 up to x sub k minus 1. We formalize this operation as digital decomposition. To ensure correctness, we need 3 checks. The first is to invoke check range to ensure each digit belongs to a given range. The second is to check these digits can be composed to reconstruct the original x. Importantly, it needs an additional check to ensure that the composed value is smaller than the modular p. The reason is that a malicious prover could decompose x into a value from a larger field rather than ZP. This situation can still pass the first 2 checks. We also give an efficient digital decomposition protocol for positive values. More details, please refer to our paper. We next present the comparison protocol. Given a private x and a public constant c, it verifies that x is smaller than c. Our idea is to use the recursive comparison. It means that x is smaller than c can be converted to comparisons between x1 and c1, and between x0 and c0. Here, x1 and x0 are decomposed digits of x, so they have smaller bit lengths. Our protocol has 3 steps. The first is to check decomposed digits using check range protocols. Then we invoke check lookup to compare xi and ci. Finally, we compose the comparison results on these smaller digits, and further invoke lookup table to check x smaller than c holds. Based on the building blocks, we further design efficient zero-knowledge proofs for complex mathematical functions, including exponential, division, and square root. We take exponential as an example. Our main idea is to first decompose x into several smaller digits, x0 up to x sub k minus 1, using our digital decomposition protocol, and then perform exponential on each of these digits using table lookup. In the last step, the outputs are multiplicatively combined to recover the real result. Finally, we apply our zero-knowledge proofs of building blocks and mathematical functions into machine learning applications. We design zero-knowledge proofs for ReLU, max polling, sigmoid, normalization, soundness, and glue. It's worth noting that our building blocks are general and can be used in more nonlinear functions beyond machine learning scenarios. Now we show the experiment results. This table gives the performance of our building blocks. We can observe that they have low computational and communication overheads. The computational overhead does not exceed 40 microseconds, and the communication overhead is less than 1 kilobyte. Compared with the recent work, our protocols for mathematical functions achieve 61 up to 129 times runtime improvement, while providing a better communication efficiency. When applied in machine learning, our protocol also achieves significant runtime improvement. For example, For the sigmoid function, the computation performance of our protocol is 100 times better than mistake. The above is a brief introduction to our work. More details can be found in our paper. If you have any questions, please contact me or Hanxiao via email. Thank you very much.